So we were talking about this example. In this example, it is a given grammar and a given string. We are trying to derive a string. So when you are trying to derive a string, always you have to start with the start symbol, which will be s. Okay. Now for this s, you can use any of these productions to replace this s. Okay. So here you can see you have all the choices, whatever you can, but you want to derive this statement or this string. So somehow you will decide to choose either this one or this one, right? No other option, I believe. So you will choose either s plus s, or you will choose s star s. Okay. So suppose you have taken the first option, s plus s. In that case, now you are trying to replace these two s's and then finally get your string a plus b plus c. So you are getting this plus symbol here. So on the left hand side of the plus you will have a, on the right hand side you will try to derive b star c. So I think this s should be replaced by a. This production, this rule, s derives a, should be used, and this s should be replaced by terminal a, and this non-terminal s should be replaced by another rule. I believe since plus symbol is already present, so now a star symbol should be used. So s star s, you will get s star s. So these two non-terminals are to be replaced. Now I believe the first s will be replaced by b, if at all possible. Yes, it is possible. Here one rule we can see, s derives b, so we are replacing it with b, and this s is being replaced by c. The similar thing we can do with this derivation tree. First of all, we have chosen this production, s gives s star s, so we have used it, and now since a star is here, so on the left hand side we want a plus b, so this will be replaced by s plus s, and this will be replaced by, I believe, c. This s can be replaced by a and this s can be replaced by b. In both the cases, from this derivation tree, if you read from left to right the terminals, you will get a plus b star c. Here also you are getting a plus b star c. However, what will happen later on, you may understand when you will see syntax directed translation. You will see what happens in this derivation tree. The operation, if at all this is an operator, then this operation, whatever operation is towards the leaf, the operation which is towards the leaf is performed first, and then later on those which are towards the root. Okay. So here in this for this derivation tree, the multiplication will be performed first, and whatever you get the result, that will be added to a. However, if this is the derivation tree, then addition of a plus b is done first and then it is multiplied with c. We all understand with the BODMAS rule that this is a correct derivation tree. However, this wrong derivation tree is also possible. Let it be whether wrong or right, these are two different derivation trees. So if there are two different derivation tree for same string, in that case we can say that the grammar is ambiguous. Okay. Compilers actually do not use these ambiguous grammars. They need the grammars which are free from ambiguity. Many a times you would have seen in your other lectures also that many a times this ambiguity is because of two things. One is left recursion. Okay. Let me write it, left recursion and left factoring. So whenever there is a left recursion or left factoring, we try to remove this left recursion or left factoring before giving this grammar to a reality or to our parser. Okay. So maybe what I want to say, before using the grammar. So since compilers need grammars which are free from ambiguity, so we try to remove the left factoring and left recursion before applying it to compiler. Now what actually happens here, given a string, you try to I am not talking about left factoring, left recursion, left factoring here. If you want, we can talk about it. You will have to tell me. For now I am telling you that starting with a string. Okay, so given a string, what you need to do, you will use your grammar. There will be a start symbol. From the start symbol you will try to derive W. If there is a possibility, if you are able to derive the W, it will be on the leaf node. Okay, all the leaf nodes together, you can see that whether W has been derived or not. If you are able to derive, then we can say that this string W is element of the language supported by the grammar G. Okay. Suppose there are two grammars. Okay. Suppose there are two grammars, grammar 1 and grammar 2. Now, is it possible that these two grammars are actually equivalent? Means, is it possible that the two grammars are generating the same language? Okay. Equivalence of grammar actually, okay, equivalence of grammar. Basically what happens here, two grammars G1 and G2 are equivalent if and only if the language of grammar G1 is equal to the language of grammar G2. Okay. So this is something that we should keep in mind. Now let us talk about something, some examples. Let us consider. Suppose I have a grammar S gives AS lambda. What does it mean? It means I can have any number of a lambda also. What can be the language of this grammar? Language of this grammar is having lambda as well as 1a, okay, 2 times a, and any number of many times a. You can also write it as a to the power n, okay, where n is greater than equal to 0. Okay, if you want to write a regular expression for it, it will be a star, you know. So while deriving something with this a star, it will be something like you will start with s, and then you have two options. You can use as or lambda. Here also you have two options, as or lambda. Here also you have two options, as or lambda. Okay, Control Z. So if you want to generate this string a multiple times a, in that case you can keep going on in this direction, and in last whatever the s remains, this s will be replaced by lambda, you know. So that is how it goes on. This is a kind of derivation tree. Now okay, given the grammar, you already know whether a grammar is a regular grammar or not. So let us see a to the power n, b to the power n. Okay, n is greater than equal to 0. So this is a language. Okay, I am not showing any grammar, it is just a language. Now my question will be, is it a regular language or not, or I will also ask what can be a possible grammar for it, a possible grammar rule, grammar production. Can you tell me a production rule for this? Any of you? You have to tell me a production rule to generate this language. Grammar. Start with S. Okay, let me write. You can start with S, and S can derive, you want A and B any number of times. So it is actually equal number of times. Whenever there is a, there is a B. Okay. It is a possibility that there may be neither A or not B, right? However, you want this to be repeated any number of times. So let me write it as in between them. So there is A and B, here it is S, and if you want more AB, so you will replace this S with the same thing. In the last, if you don't want further, you will replace this S with lambda, right? So this will be a possible grammar for this language. Now you have to tell me whether it is a regular grammar or not. Can you tell me this grammar, is it regular or not? Okay, I have to name somebody, right? Rohit Negi. Rohit, can you tell me this grammar is regular or not?
So yes, because we can convert it AB whole star, and mean star can show like we can use lambda and any number of times AB.
If I remember, maybe the last or previous class, we were talking about 4 types of grammar: type 0, type 1, type 2, type 3. Can you tell me which type of grammar it is? It is type 0, type 1, type 2 or type 3? Rohit. Let me ask this question to Aman Kumar. Aman, tell me which type of grammar it is.
Type 0, sir.
Why? Is there possibility of having any higher type of grammar?
No, sir, I guess.
It cannot be type 1 grammar.
So the left hand side is not equal to right hand side. The number of variables.
Let us see the same thing. Let me ask uh, Himanshu Raj.
Yes, sir.
So, what do you think? What type of grammar it is? Type 0, type 1, type 2, type 3. Highest possible type. Himanshu Raj.
Yes, sir.
So, you don't know it.
No, sir.
You were not present in that class.
No, sir. I was absent last time.
Sabir Khan. Sabir Khan, can you tell me
Yes, sir.
which type of grammar it is?
Sir, it is type zero. It it's not a regular grammar because automation is not finite. It is type zero because it's unrestricted.
Okay, let us ask to Satyavrat. Satyavrat, what do you think?
Sir, it is type 2.
It is type 2 grammar. Let me ask this to Sai Teja. Sai, what do you think?
Yes, sir. Sir, can we write this as ABS?
You can write it as ABS, but if you will write the language, it will change. It will not remain A to the power n, B to the power n. It will become AB to the power n.
So I think type 2.
It is type 2 grammar.
Yes, yes.
Rishabh Kumar, what do you think? What type of grammar it is? Rishabh Kumar. Rishabh. Okay. Vivek Kumar.
Yes, sir.
So, what do you
So it
think?
will be type 2, sir.
It will be type 2. Some of the students were
Yes,
thinking
sir.
it cannot be better than type 0. So, do you think it will be really type 2 grammar?
Yes, sir. It will be type 0 because here we are generating recursively, sir. Then maybe type 0.
See, while thinking about type 0, type 1, type 2 or type 3, you have just to see the rules that we have seen for type 0, type 1. It is so simple. Okay. So, for type 0 it was unrestricted, means there was no rule. So every grammar possible will be type 0 grammar, every possible grammar, whatever you write. Okay, so if you are not able to find anything, it is a type 0 grammar. For type 1 grammar, it was very simple, just one restriction, that on the left hand side, whatever it is, it should be the size of it, the length of that particular thing in the left hand side should be less than the length in the right hand side. So here you have two productions, you can see S gives ASB and S gives lambda. S gives lambda is always allowed, no problem. Other than that, S gives ASB for this production also. In the left hand side, it is the length is 1, on the right hand side the length is 3. So it is also allowed in type 1 grammar. Now let us check whether it is possible for type 2 grammar. So for type 2, what it was? For type 2, it was that in the left hand side you will always have one single non-terminal, okay, or variable, whatever you call it, variable or non-terminal. So on the left hand side, one single non-terminal. So here you have two productions, S gives ASB and S gives lambda. In both the cases, on the left hand side you have single variable. So it is a type 2 grammar. Now let us check whether it can be type 3 grammar. For type 3, it was that you can have on the right hand side, on the left hand side it was already done in the type 2 grammar. So it should follow all the rules of type 2 grammar, as well as more restriction was that here on the right hand side either it should be all terminals, okay, either it should be all terminals, only A, B, A, B, A, B kind of things, then it is okay, or it can be terminal, any number of terminal and a variable. This is also a possibility. You can also have a variable and then any number of terminals. So all these three things, any of these three things is possible. Okay, this is always possible, no problem. But these two, among these two, any one of these can only be possible, not both of them. Okay. So we have seen that there are two things, S gives AA and A gives AB, BB, whatever we have seen. So you can see the variables are on this side, right side. So this is right linear, okay, one single variable in right hand side, this is allowed. Okay. Similarly, S gives AA and A gives BB, this is also allowed. However, if you have something like S gives AA and A gives BB, so in this case what happens, you are having these two, both of the things, so this is not allowed in regular grammar. So this was a story of something that you can match. Here what is happening, this is not at all in the rule any of these three, right? It is neither this nor this nor this. Okay. Here it is what, in between you have a variable and on the side you have non-terminals, terminals. So it is something like T, V and then again T, right? So this is never allowed, this can never be allowed in regular grammar, type 3 grammar. So this is not a type 3 grammar. However, it has satisfied all the rules of type 2 grammar. So highest possible type is type 2 grammar. Type 2 grammar. Type 2 grammar was context free grammar, CFG. Now what I was actually telling here is, a grammar may not be regular. Now this language, whether this language is regular or not. Okay, no idea. So this language is also not regular. But what I was trying to say is, sometimes it is possible to write a language or grammar which is not regular for a regular language as well. Okay. So as you can understand, type 3 grammar. Okay. So for a type 3 grammar, you can write a type 2 grammar, equivalent type 2 grammar. Okay. However, you cannot write equivalent type 3 grammar for type 2 grammar. Okay. You can always write a type 2 grammar for type 3 grammar. Okay. But you cannot write a type 3 grammar for type 2 grammars or languages. So what I wanted to say is, type 2 is context free grammar. So it is actually written for context free languages. So this language that you have seen was context free language. So for every language, suppose I want to say for every type 3 is for a regular language. Okay. So let me write it as like this: for every regular language, there exists a context free language or a context free grammar. Okay. However, let us see, for every context free language, there exists a regular language. Is it possible? This statement is true. This statement is actually false. For every context free language, you will not have a regular language. You would have seen when in your automata class that there is part which can be called as a regular language, and this is a set of language which is context free language. So definitely the regular languages are part of context free language. However, there are certain context free language which are not regular. So you can say that for not every, for some CFL there exists regular language. Okay, this is correct. So similar is the story of grammars, that for some context free grammars, regular grammars can be possible. For every regular grammar, context free grammars are possible, but not for all context free grammars, regular grammars would be possible. So let us take a few more example, and then we can move further. Suppose S gives AA, and this S gives another A, B, or it can give AB. So you have to tell me what will be the language. Okay, this thing actually this is not S, this is A. S gives AA and this A gives like this. What will be the language? Am I audible?
Yes, sir, you are.
Okay, so you all have to try what can be the language for this grammar. Language is a set of strings, that these are the strings which are possible, right? In the last example, as we have written, it was S gives A, S, B and lambda. Then we found that the language of grammar is something like A to the power n, B to the power n, where n is greater than equal to 0. This was something that we found. So here in this case, can you find what can be the language of this grammar?
A B B.
You can have A
A, B B.
B B. This is a possible
Yes, sir.
string. You are saying this is a possible string which can be accepted by this language. Okay,
Yes, sir.
given the grammar. Is it? Can we have some more?
Yes, sir.
Sir, A power n, B power n minus 1.
Okay, you are saying A to the power n,
B to the power n minus 1.
B to the power n minus 1, where n is, what is n?
Greater than equal to 1.
Greater than equal to 1.
Wait, no.
No, no.
It can be 2.
2.
Yes, sir.
Yes, sir.
Okay. So if it is 2, it means that the least possible string is A to the power 2 and B to the power 1, which means AAB. Is it so?
Yes, sir.
The smallest possible
Yes, sir.
string.
Yes, sir.
Yes, sir.
How is it possible? Starting with S gives AA, you have one A and this A
Sir,
is, tell me.
Yes, sir.
A gets
AAB.
substituted with AB.
A is replaced with this AB, है ना? Yeah, correct.
Yes.
Yes, sir.
So in this way you can get
Yes, sir.
smallest possible AB. So definitely this is your language for this grammar. Can we take one more example? Suppose if you write something in between it, like S gives AB, A and BA, and this A will give you suppose same thing AA, ABA, as well as something it can be replaced with something CC. Suppose this alphabet was having A, B and C, no problem. So what can be the language of this grammar?
Production, it is AAABA or ABABA.
Okay, tell me, I am writing whatever.
That production.
Okay, you want to change something in production.
King is correct, like आपने बोला था same होगा.
नहीं सेम नहीं, या
जो
करेक्ट है, ये ऐसे ही बोला मैंने, यही सही है, चेंज किया मैंने यहाँ पे, ठीक है.
ओके.
क्या होगा लैंग्वेज? एक स्ट्रिंग लेता हूँ मैं, देखते हैं वो स्ट्रिंग इस लैंग्वेज को सेटिस्फाई करता है या नहीं. मान लो आई हैव ए बी, देन ए, then CC, then I have BA, BA, BA. Okay. So is it a possible string from this grammar?
Yes, sir. Yes, sir. It's possible.
It is possible, eh? Okay, let me take
Yes.
another string. It can be something like A, B, A, C, C, B, A, B, A, B, A, B, A. Okay. Is it possible?
Yes, sir.
Hmm?
Yes, sir.
Is this string possible with this grammar?
No, sir.
No, sir.
Any good reason?
Sir, if the, if, uh, if the number of BAs are increasing on the right side of CC, it
Okay.
also increase on the left side.
So what do you want to say? They should be equal. Hmm?
There should be AA to the left of CC. So yes, sir. I think number of AAs and BAs are equal.
Number of AA and BA should be equal. Okay. AB is counted or not? BA, BA. Now I believe number of AA are equal to number of BA. Is it acceptable now?
No, sir.
No, sir.
Still not acceptable. Now what is
Sir,
the problem?
actually we have to count it.
You have to count?
Sir, language would be like A to the power n, then CC, BA to the power n plus 1, where n is 0.
Okay, repeat, let me write here. A to the power
Sir, AB.
A to the power,
Not in power,
okay,
simply AB.
simply AB,
Then A to the power n,
A to the power n,
and then CC,
CC,
then BA to the power n plus 1.
BA to the power n plus 1. Okay,
And n is greater than equal to 0.
n is greater than equal to 0. Oh, so let us think about smallest possible string with this. Let us keep n is equal to 0. In that case this will be 0 and this will be 1, right? We will get AB to the AB, CC and BA. Is it so?
Yes, sir.
So is
Yes,
it
sir.
possible with this grammar?
Yes, sir.
So for this string what we will do, we will start with S, we will keep AB, A and BA, and this A will be replaced by CC only, है ना? In this case we will find this thing. So here what is happening, one AB and one BA is from here, and here we can see that it is AA and BA repeated same number of times, and in last A is replaced by CC. So it is CC and AA and BA will have same number of time. If it is N, then this would also be N, and in last we have one BA, that's why it is N plus 1. Very correct. This is the required language for this grammar. So now I think you are able to find the language for given grammar. Okay. You have just to tell me what will be the possible language for this grammar. I believe this part is already seen. You have AB, A and BA.
Yes, sir. Sir.
And A can be replaced by the same thing. So yeah, tell me, you are telling me something.
Sir, AB,
Let me write AB,
A to the power N,
AA to the power N,
then CC,
and CC,
and then BA to the power N plus 1,
BA to the power N plus 1,
A to the power N,
A to the power
N, N, N.
N.
Yes, sir, where N is greater than equal to 0.
N
Will
is
be
greater
N
than.
plus 1.
This should be.
Oh, no. Sorry.
Okay, let us check it out whether it is able to generate the possible strings or not. Let us take an example for the string. Suppose it was AB, then CC and BA and AAA. So this string, is it possible with this grammar?
No, sir.
Okay, let me check. This was the smallest possible string from the last example, as we have remember. I have replaced S, starting with S, I replaced S with AB, A, BA, B, and then I replaced A, and for replacing A,
Sorry,
I
sir, there
used
was a
CC.
mistake.
CC, BA,
A to the power M.
A to the power
Another variable
any other variable. Okay,
where, yes, sir,
okay, suppose
be greater than
K.
equal to 0.
So
Greater than equal
K
to 0.
is also greater than
Then
equal to
it
0.
is
Huh?
accepted. Yes.
Yes, this is a possibility. So if it is here, as we can see now, B is going to be replaced. So here we can see that B is producing A star, any number of A. So definitely this is a possible string with this grammar, and with this language, definitely this language is correct now. So this is something that we have seen till now. Now we can move further. You all are aware of these automata machines, finite automata, basically like DFA, NFA kind of things. Before moving that also, if I this thing you would have seen in automata, but let me write here that if you want to recognize language language from grammar, you will have two methods. One is substitution, and another is converting into machines. Okay. Substitution is what? This is the way what you have done here. You started with your starting variable and then you substituted it, and somehow you tried to figure out what it is, and then you have generated the language. That if you want to replace a, then it is something like generating this kind of thing. So you have replaced the a here with this particular language. So this is called substituting. If you want to go for converting into machines, what you can do, this was a bigger example. Let me take a small one. S gives suppose a b. Okay, no, as only, control z, as lambda. So for one variable you are making one state. Okay, and for this state you will try to see, given the non-terminal, what is the transition. It is saying if a is coming, so on a you will go to a state s. So on a you will go to a state s. Another production rule is saying s gives lambda. That means this is the final state. So it is something like this. So by seeing this machine, you can understand what it is doing, right? It is actually accepting any number of a's. Okay, so it is something like a star, right? It is a regular expression. If you want to write something else, you can write a to the power n, where n is greater than or equal to 0, right? This is also a possibility. Suppose you want to have another example, 2 more a's. Okay, let me give you an example like it is we want to have 3 a's. Okay, and then s and then lambda. Okay, so what happens? You will have s. From this s you will have a, and you will have to move further a state which will further give you 2 a's. So from here also you will get a and a new state. From this state you will get a and you will reach to the state s, right? So like this. Okay, and another production is s gives lambda. So this is final state also. Okay, this was your starting state as well as the final state. So for this you can easily understand that it is AAA star. Okay, so this is the story of your grammars. Now I have to understand in the next class whether I have to tell you something about DFA and FA, or shall I now start moving and coming back to our compiler where we will see some more things in lexical analyzer. Here actually we went through this grammar and irregular expression just to understand the regular expressions. We have seen some of the regular expression. When we will come back to compiler, we will see some more regular expression, that this is valid, whether this is commutative or not, associative or not, whether the epsilon is the identity operation or not, kind of these things. What is idempotent operation? We will see these things here when we will come back to the compiler. But we will also see you have to see lex and yak. So for that also we will see in lex actually how these regular expressions are represented. So basically after that we will be able to start our lex programming also. Lex is actually I should say a tool for you to generate lexical analyzer automatically. You will have just to specify the patterns of your identifiers along with the keyword also. If there are keyword, how they are defined I will tell you. You have to define the patterns, that these are the patterns which you should match, and accordingly you can generate and this tool lex will help you in automatically generating a code that can tokenize your input file. Okay, so this lex program will make it very easy for you to work with. So I was trying to understand, you are aware of DFA or not? DFA and FA kind of thing. You have to tell me, otherwise I will understand yes you have already studied, no? Formal automata kind of subject was there, I have seen.